So polymers, which is what I'm going to talk about today, is not going to be on the third exam, but there may be problems on the ACS exam that are related. So, anybody have a definition for polymers that's in their mind? How do you know if something is a polymer? There are biological polymers, right, that you're probably familiar with. DNA is a polymer. Proteins are polymers. What pops into mind when you hear the word polymer? We were doing a word association game. What's the first word that comes to mind?
Something that's made up of a lot of smaller things.
Yep, so that's the key to polymers. Right? They're long chain molecules composed of repeating units. And the type of polymer we're going to talk about today is an addition polymer, which are also called chain growth polymers. Chain growth is the more technical term. And the repeating unit, the monomer unit, is an alkene, which is why we're talking about it, because we're in the alkene chapter. And the reaction, obviously, is an addition reaction. So we already know a little bit about addition reactions. And the chain growth polymer comes from the fact that it's built up link by link, one monomer at a time. Like chain links. There are also a set of polymers called step growth polymers, which are condensation polymers. Those are usually reactive functional groups like carboxylic acids and alcohols and amines and things like that. And they don't add one by one. They'll make one large unit and another large unit, and then there'll be a sudden increase in viscosity as those two large units join. So, repeating units, right? That's one of the things that popped into your head. What other words, if you were doing word association, might you associate with polymers? There's one I'm looking for that hopefully someone can.
This might be way off, but I think of rubber.
Okay, rubber. Anything else? Rubber is in fact an addition polymer.
Large.
Yep, long chain. There are various forms of rubber, but you haven't come up with the word that I think most people probably associate with polymers. You came up with rubber, which was surprising, because I would have thought you would have come up with the other one first. Anybody have a drink bottle in their hand right now? Or on their desk?
Plastic.
Plastic, right? That's the word that I think usually people associate with polymers, because plastics are polymers. So all plastics are polymers, but not all polymers are plastic. Plastics is a subset of polymers, which comprise just ones that can be heated and remolded. And in principle, multiple times. So they're actually called thermoplastics. That's one of the types of polymer, because you make them plastic, right? That ability to mold them is created by heating. So thermoplastic polymers is one example. And all of the addition polymers that we're going to be talking about today are, in fact, thermoplastics. The other type of polymer is called thermoset, and thermoset polymers are things like superglue and epoxy, where the polymerization reaction occurs and it generates a hard, usually a three-dimensional or two-dimensional lattice that then can't be made flexible by reheating. So once you have a thermoset polymer, it's usually not recyclable or reusable because you can't change the physical properties through heating. So let's consider just a reaction of a simple alkene. And I'm going to use as the example isobutene. Which is also called isobutylene. Isobutylene is the common name. Isobutene is the one of the IUPAC names. What would be the real IUPAC name for this compound? Isobutene is also kind of a common name. There will be potential naming questions on the ACS exam, so that's one of the reasons why I'm doing this. And we're
2-methyl 2-propene.
2-methyl 1-propene. You don't really have to say 1-propene because there's only one way you can put that double bond on there. Alright, so you'd number it like this, and there's a methyl group in the 2 position, the double bond starts at 1. You always name the alkenes with the first carbon of the alkene. So we're going to take 2-methyl 1-propene and we're going to react that with catalytic acid. Let's say we put in concentrated sulfuric acid, and there's a little bit of water, right? Because sulfuric acid is about 98%, which means there's about 2% water in there as well. So if I were to put this question on the exam, give you this reaction and ask you to fill in the product and provide a mechanism, what would you do? What would be the first thing you would do for the mechanism of sulfuric acid reacting with 2-methyl 1-propene?
Get rid of the double bond. Have the double bond attach something.
Yep, what's something?
The water.
Water is neutral, and it's not a very strong acid. And in fact, there isn't really much water because sulfuric acid is a strong acid. So that sulfuric acid is going to dissociate. It's going to react with any water that it can react with to form the hydronium ion and the hydrogen sulfate ion, with a pKa on the order of -3, I think, or maybe -6. But there's 98% sulfuric acid and only 2% water, so there probably isn't very much of the hydronium ion around. There's a lot of sulfuric acid. So in this case, with concentrated sulfuric acid, the logical acid source is the sulfuric acid itself. So we would protonate that. On which end of the double bond would we protonate? So this is the electrophile, right?
Hydrogen.
And the electrophile always goes to the less substituted end. So we're going to do that. We're going to protonate this, form an additional methyl group, and the most stable tertiary carbocation. Right, so, and then obviously the hydrogen sulfate ion as well. So we've got this tertiary carbocation, hyperconjugation stabilizes it. What would be next? Well, if you were in dilute sulfuric acid, right, the next step would be water attacking the positive charge, because in dilute sulfuric acid, maybe like 6 molar, we get an addition reaction, and the reaction is to form an alcohol by the addition of water across the double bond. Right, so that would be the next step, and then we do a proton transfer at the end to form tertiary butanol. But you're not in dilute sulfuric acid, you're in concentrated sulfuric acid. So we have this carbocation. What can it react with? The hydrogen sulfate ion is not significantly nucleophilic, so it's not common for the hydrogen sulfate ion to react with things.
The pi bond of another alkene.
Yep. So in the absence of any nucleophile, right, any added nucleophile, it's the same nucleophile that we use to attack the sulfuric acid can attack this carbocation. And it will do it the same way. So we'll form a new carbon-carbon bond to the CH2 group. And then we'll have a new tertiary carbocation. Now what might happen? You notice I drew this first reaction as an equilibrium. So sulfuric acid can protonate the double bond to generate the hydrogen sulfate ion, but the hydrogen sulfate ion could come and take that hydrogen right back off and take us back to the alkene, which would be what you would expect if you were to take the tertiary alcohol and dehydrate it. And concentrated sulfuric acid often creates alkenes by an E1 elimination of water. So if the sulfuric acid anion, the hydrogen sulfate ion, were to take a proton off, where would it take the proton from? There's probably a reason why I drew that hydrogen particularly big, and I put this oxygen near it. So you would expect that you would be able to dehydrate to form the CH2 here, or to form a CH rather, and a double bond. And this is a dimer. Right? It's composed of two of these repeating units. You've got a hydrogen on the end, so that double bond's not there anymore, but it's two isobutene units attached to each other. So that happens, and you can probably isolate that dimer. But it doesn't necessarily have to stop there either. Because if you are isobutene, you probably can't tell the difference between this carbocation, which is a tertiary carbocation, and this carbocation here, which is also a tertiary carbocation. So there's no reason why another isobutene couldn't then attack that, and you could end up having three isobutene units and making a trimer. So this is an acid catalyzed polymerization process. And it works because we've got electron donating groups on the alkene, and those stabilize that charge. Right, on the tertiary carbon. And really, the length of the polymer depends on the yield of the reaction. So if you start with isobutene, the key to a successful acid catalyzed polymerization is to give it an acid. It could be a proton source, or it could be a Lewis acid. Doesn't have to be a bronzoside-Lowry acid, right? So the A is going to react to form the tertiary carbocation, and then that's going to go off to the races and keep polymerizing. If that reaction is a 90% yield for the addition reaction, what's the maximum length of polymer that we can get? So if I say something's a 90% yield, right, and I do 10 reactions, how many of them work?
9.
9. So how many fail?
1.
So 1 in 10 reactions fails, right? If 1 in 10 additions fail, what's the maximum length of polymer? Basically, every 10th reaction fails, and instead of adding another monomer, it does this and dehydrates. Right, so you'll get 9 successive reactions. The maximum polymer length is 10 units on average. One thing that's true about these polymers is the polymer is a mixture of a whole bunch of different chain lengths. So we talk about the average molecular weight, not the molecular weight, and the average molecular weight determines the properties of the polymer. That's not quite true, actually. It's a little bit of a lie. Because there are a bunch of different ways of calculating the average molecular weight. And what's true of polymers is the properties of the polymer are heavily dependent on the longest chains in the polymer. So we do a weighted average where the longer chain polymers contribute more to the average molecular weight than the shortest chain polymers. And that's similar to what you see with the average distribution of molecular speeds, where the really fast moving, high energy materials play a larger role in the properties of the gas, for example. And you probably remember talking about the root mean square velocity as opposed to the average velocity. And the root mean square velocity is the one that's proportional to the kinetic energy of the system. So it's a similar system with polymers, and there are 3 different weighted averages that give a different kind of importance to the longer chain polymers. But it's very important to have a high yielding reaction if you want a long chain polymer. And to get desirable commercial properties for the polymer requires long chain polymers. So we need a high yielding reaction. 90% yield is nowhere near good enough. So polymer chemists spend a lot of time just trying to improve the yield by 0.5% from, say, 99% to 99.5% or 99.5% to 99.7%, because that small increase in percent yield can provide dramatically different properties of the polymer. So acid catalyzed polymerization is one of the ways that you can start a polymerization, but there are other ways you can start polymerization. You can do radical polymerization. So let's say I were to take vinyl chloride. So this is the vinyl group here, right, which you saw that typical ABX pattern, but now we got a chlorine on there. What would be the real name of this?
One chloroethene.
Yep, or just chloroethene, because there's only one way to put that on there. So if we took vinyl chloride or chloroethene and reacted this with HBr in the presence of T-butyl hydroperoxide, what would be the reaction? what would be the mechanism, what would happen if we just heated this up? A little bit of diterbutyl peroxide. This reaction could be on the exam. Hydrogen bromide, chlorethene. I should have had a quiz today.
Anti-Markovnikov addition.
So the anti-Markovnikov addition. So the first step is to break that weak bond, generating the T-butyl radical. T-butyl radical then plucks off the hydrogen to create T-butanol and bromine. So that's the initiation. There's two steps, right? Step one of the initiation is breaking the peroxide. Oh, stop that. Can you see this again, or did the screensaver fuck everything up? You still seeing my pages?
We can see it.
Okay, good. The screensaver, I got to it before it fucked up. So we got the bromine radical. This is now the electrophile. Where's that electrophile going to attack? What's the great truth of electrophilic addition reactions? Whether they're Markovnikov or anti-Markovnikov, which end does the electrophile end up at?
The less substituted end.
Yep, so the bromine's going to be here. The electrophile is always on the less substituted end. Markovnikov additions, the electrophile is the small thing. Anti-Markovnikov additions, the electrophile is the large thing. And this radical is stabilized by hyperconjugation because we got an adjacent chlorine. Right. And then what would happen? So this is propagation step 1. This is addition step, or initiation step 2. Right, and initiation step 1 was just the formation of the hydroperoxide radical, the terbutyl radical, sorry. So what would be the next propagation step? Keep in mind that the 2 propagation steps has to add up to the overall reaction, which means that my next propagation step has to regenerate that bromine radical so that it can go back into the first propagation step. So to generate that radical again, I'm going to use this to pluck off that hydrogen. And then propagation step 2 would be to form the carbon-hydrogen bond, and the net effect would have been to add HBr in an anti-Markovnikov fashion, so the bromines are less substituted end across that. Right? So let's do that same reaction but this time let's leave the HBr out, so that all we have is the T-butyl hydroperoxide, or the diterbutyl peroxide, and heat, and no HBr. The paper keeps curling. That's so you can still see it. So what's going to happen if I just heat a mixture of vinyl chloride and diterbutyl peroxide? I think you can answer that. I think lots of things. Sometimes they're...
There'll be the terbutyl radicals.
Nothing's going to happen to the initiation step, right? That can still occur because that's still a weak bond, about 39 kilocalories per mole. So we get the terbutyl radical, but now there's no HBr for it to pluck a hydrogen off, so what does it do?
Take a hydrogen from the alkene.
Not as likely, because these are sp2 carbon hydrogen bonds, which means they're significantly stronger than the sp3 hydrogen bond. right? This can definitely take hydrogens off an sp3 hybridized carbon because the OH bond is stronger than the CH bond for an sp3 CH bond. But the sp2 CH bond is quite a bit stronger because of the greater S character. Not illogical, right? So hydrogen abstraction is one of the things that that radicals like that do. What happened in propagation step 1 here?
The pi bond could attack the radical?
Yep. So there's no bromine radical, but there is the terbutyl radical. So there's no reason why the pi bond can't attack that. To put and form the same resonance stabilized radical that we had here. Right. But now there's no HBr, right? So there's nothing for that to take a proton from, so what's it likely to do?
Repeat itself with another alkene.
Yep, and we can form a polymer. And we'll get this polymer in what we say is a head-to-tail manner, because the radical, whether the radical is that oxygen radical or this new carbon radical, is always going to end up at the less substituted end. Right, and then this can happen again, and it can keep going. So as long as you don't have any side reactions, you can continue to build up your polymer, and you'll build it up so that the repeating unit always looks like this. Right, so it's a long chain, and we've got this CH2CHCl. You'll notice that when you look at these addition polymers, they're all sigma bonds in the polymer. The pi bond is gone, right? The polymer doesn't have pi bonds. And we've got our terbutyl radical over here, and then something's going to happen, right, to end it. So what can end the polymerization process? Well, you already answered that question. One of the problems with this kind of polymer is once you start building up this chain, and you've got these CH2 groups in the middle. Now they're sp3 carbon-hydrogen bonds. You always have to worry about either the T-butyl radical or some other radical plucking off one of those hydrogens and doing hydrogen abstraction. And that's going to generate a radical somewhere in the middle of the chain. And this radical in the middle of the chain is going to lead to branching. There are some situations where you might want a branched polymer, but usually you don't want a branched polymer. Usually you want your polymer to be nice and linear, because that's what gives it the high molecular weight and the uniform properties that cause it to be commercially desirable. Right? Branched polymers are usually more flexible, with lower melting temperatures. Right, and other different physical properties. Right? So radical polymerization works, and it works well when you have something that's going to stabilize the radical, like this chlorine on there. Another way we can do polymerization is anionic polymerization. And one of the polymers that proceeds by anionic polymerization is superglue. Right? You've actually got some hydroxide, small quantities of hydroxide, and then your monomer for superglue looks like this. It's got a nitrile, and it's got a methyl ester. So this is called cyanoacrylate, methyl cyanoacrylate. Acrylic acid is this structure. Got the carboxylic acid here. What would be the IUPAC name for that? And so this is methyl cyanoacrylate because it's the methyl ester of acrylic acid, and then there's a cyano group attached to the other carbon. So we would number it like that. Carboxylic acid gets number 1 because it's the most oxidized carbon. And this would be 2-propene oic acid. So 2-propenoic acid is acrylic acid. This is methyl cyanoacrylate. So if you were asked for a mechanism by which methyl cyanoacrylate would react with hydroxide, how would you start? Where is this hydroxide likely to attack this cyanoacrylate? There are a couple of good answers to that question.
I think either at the carbon with the cyano group,
Okay, so
or the double bonded oxygen.
So that's an electrophilic carbon, and that's an electrophilic carbon because they're both attached to a electronegative element that's pulling electron density away. Those are the two answers I was expecting. But the other thing hydroxide can do is it can attack this carbon, because by attacking this carbon it can push this double bond either towards the oxygen or towards the nitrile. And this is called a 1,4 addition. It's very common when you have a double bond in conjugation with, right? So if I were to just attack this and move the pair of electrons onto the carbon, we would generate this anion. But then that anion can be resonance stabilized by donating out to the oxygen or donating out to the nitrogen. So we've got electron withdrawing groups now instead of electron donating groups. So instead of stabilizing the positive charge, we're going to stabilize the negative charge. But it's the same principle, right? The thing that initiates the polymerization reaction what did I just do? That hydrogen's not there. That hydrogen is a nitrile. There we go. Right. So we've got this resonance stabilized ion or material, and it can also resonance stabilize by pushing that pair of electrons out onto the nitrile. So we would get this substance. And it's more stable to put the negative charge out on the nitrogen or the oxygen. So we've actually got 3 resonance structures. One of which has the negative charge on the carbon, one of which has the negative charge on the nitrogen, and one of which has the negative charge on the oxygen. Okay. So if this negative charge here were to react with another molecule of cyanoacrylate, one of the annoying things about polymers is they're big molecules, so there's lots of writing. We could do a head-to-tail addition just like we did before, right? This negative charge could attack the unsubstituted end, and it can push this pair of electrons out onto oxygen, and we can continue to grow the polymer. Right. So the type of polymerization reaction you use depends on what's attached to the double bond. If we've got a pi bond that has an electron donating group here, right, we're going to use an acid catalyzed. And if we have something which is an electron withdrawing group, we're going to use an anionic or base catalyzed. Polymerization reaction. And then radical reactions can do even unsubstituted, right? So if we just had the parent ethene, which is also known as ethylene, we could do a radical polymerization, because radicals are very reactive. They don't really care if there's something to stabilize them, and we would make polyethylene, which is number 2. If you are for HDP, that's high density polyethylene, which is very linear, and number 4, which is low density polyethylene, which is the branched one, which is much more flexible. Right. So those are 3 of the 4 different types of polymerization reaction. There's another one which is metal catalyzed polymerization, which involves a catalyst called the Ziegler-Natta catalyst. And the Ziegler-Natta catalyst is a mixture of triethyl aluminum and titanium tetraisopropoxide. And that one is interesting because it generates very long linear polymers. These guys won a Nobel Prize for that. There's several Nobel Prizes that have been associated with polymer chemistry. And as I said, that's a mixture of titanium tetraisopropoxide. So titanium OIPR4 plus triethyl aluminum. It's kind of dangerous because that is pyrophoric. So it's liquid fire. It ignites in the presence of air. And what happens is you create a metal surface, and the pi bonds attached to that metal surface. They like to bind to the metal surface. You've seen that in catalytic hydrogenation. And so you can get these monomers to line up on the metal surface. If you're familiar with the process of protein synthesis, right, you have the ribosome, and you have your messenger RNA attached to your ribosome. Right, so you've got your, say, T, A, G, G, C, T, and then your transfer RNAs come down to an amino acid. So your transfer RNA might be the complementary sequence to that TAG. So you might have A, T, C, and then over here you have C, G, A, right? And each of those would be attached to an amino acid. And so those amino acids would be lined up next to each other by this messenger RNA, and then you'd form a bond between the 2 of them. So it's very similar. The pi bonds attached to the metal surface, and that lines these guys up, and then they can zip up the monomers and avoid branching. All right, so this Ziegler-Natta catalyst, this metal surface catalyzed, is a way to generate nice long chain polymers. Is this familiar? Have you seen this kind of messenger RNA binding to a ribosome with the transfer RNAs recruiting the amino acids. I don't know how many of you have had a cell biology class, but that's where I would have expected you to see that. So let's take a little break. I'm going to try to save this video, and then we'll go through the PowerPoint and I'll show you some examples of polymers, and we'll consider how those polymers are likely to be made. What you really want to be able to do with polymers is, if presented with a monomer unit, you'd like to be able to show what the structure of the polymer would look like, and you'd like to be able to say whether it's likely to have been made by acid catalyzed or base catalyzed or radical polymerization or metal catalyst. And if you see a polymer, you'd like to be able to figure out what monomer unit it came from by identifying the repeating unit, right? So if I were to give you, for example, a polymer that looked like this, with a benzene ring, you'd like to be able to back out of that, identify the repeating unit, and then determine what monomer it comes from. So what you would see is you'd see CH2CH phenyl, right? And then CH2CH phenyl. So there's the repeating unit. So what's the starting material for the polymerization process if that's the repeating unit? And keep in mind that for addition polymers, the starting material is always an alkene.
Radical polymerization.
What's that? Radical polymerization would work. So would acid catalyzed, because the benzene ring with those extra pi bonds can stabilize the positive charge here as well. This is polystyrene, by the way, which is number 6 on your recycling codes. But what was the monomer unit? Well, there's a hint, right? Since it's called polystyrene, the monomer unit is probably styrene. And styrene is vinyl benzene. So you'll notice that that's the bond between the repeating unit, which is the new bond that's formed in the polymerization, which means that this used to be the pi bond. So I'll basically just break all those bonds that are between the monomer units and reform the pi bond. So styrene or vinyl benzene is the monomer unit. Right. So it's not too hard to identify the repeating unit and then just put the double bond in between the 2 carbons of the repeating unit to predict where the monomer comes from. Sorry. Now we're going to take a break. So at about 9:20, you can come back and I'll show you some